All right. Can you guys see my slide? I guess you can. I can see it through the video.
Yeah.
Is it right? Yeah. Okay, great. All right. Just like Eric, I would like to thank the organizers for enabling remote participant. This is really critical because it's virtually impossible for us to travel at the moment. All right, let me switch my camera, which is totally strange at the moment. There we go, much better. Okay, so Eric's talk set up my talk actually perfectly because I'm gonna talk about something very similar, modeling stellar oscillations and also granulations with Gaussian processes. In this case, not for the sun. And quite a lot of questions I think have been answered by the study on the sun, but we're actually targeting different stars other than the sun. All right, so this is part of a project called the RVX TESS. We have a website, please check it out, where we gather a bunch of photometric observations from either Kepler K2 in the old days, and then now TESS, and together with some ground-based radial velocities to study stellar jitter. And the thought behind, the philosophy behind this project is that we observe the star, and the star has both photometric variation and RV variation, and we believe that they are probably of similar physical origin, so they are similar in terms of time scale and amplitude, which are great for fitting them both with the Gaussian process. All right, just a quick show of our telescopes. So we had initially a bunch of data together with Kepler K2 when it was looking back in a patch of sky where we could do simultaneous observation for the first time other than the galactic center. And then we moved on to the TESS era and gathered a whole bunch of other stuff, data with sort of slightly different science goals. Unfortunately, I was heavily distracted by chasing test planets and other stuff in the past few years. That progress on this project has been slow, but I would like to share sort of a tally of what the data we have gathered, and we very much welcome collaboration and exploration on this data. So please check out our website. So we have data on 5 subgiants plus a couple of giant stars by now, both with K2 and also with TESS. To probe oscillation and granulation, and we have observed one young G-dwarf that has lots of flares to study what effects that could have, and also the rotation signals due to magnetic activities. And we have some data on Sigma Draconis, the classic RV standard star, simultaneously with TESS, to see if we can dig up any sort of oscillatory signal on that K-dwarf, which would probably be challenging. And we have 4 K-dwarfs that we hope to see some magnetic activity signals to see if phased information simultaneously with the photometry provided in space would provide any additional boost. We have not done that yet, besides finding a binary star. Binary stars are everywhere, unfortunately. And we have 3 M dwarfs observed simultaneously, either with spiral, with polarimetry, or NUID, to explore things like whether LSD measurement or Zeeman Doppler imaging could help teasing out more activity indicators to help you model stellar jitter. Okay, but today I'll focus on just stellar oscillation and granulation. So the motivation is pretty simple. As we've seen in the sun, also stars like Alpha Centauri, and also the classic paper by Xavier, that if you beam things down very nicely, so this is the plot on the lower right. If you beam things down by doing repeated observations, a longer exposure time, you can actually beat granulation and oscillation noise by orders of magnitude. So that's pretty nice. So one of the questions was, okay, should we model this or should we average this? I think the answer has been converging towards we can probably averaging out stellar oscillation signals by just having a longer exposure time on the order of like 1 over nu max of the oscillation. So this is another paper by Chaplin et al. Doing a more careful work for a group of a variety of stars at different evolutionary stage. So this is a plot of effective temperature and the integration lengths they recommended from theoretical calculation for different stellar masses to detect Earth's analog around the star. So as you can see for the sun, something like 10 minutes is already sufficient. So this is really great. But we really want to check it out with real observations, especially back then before we were more confident with the fact that we can detect this by binning things. All right, so we started with the subgiant, observed the Kepler K2, and simultaneously with Keck Harris. So the lower right plot right now is a 2-day light curve plot from K2. So K2 observed, of course, for much longer, for 80 days. But already within this 2-day data, you can see a clear oscillation signal from this subgiant star, right? And we feed a Gaussian process model to it using Cellularity, and it was very easy to feed the data. It was a piece of cake. Although there were free parameters, we did not start with the theoretically predicted oscillation quality factor or things like the characteristic frequency like nu max or anything. We just let it flow, let the data tell us, because back then the stellar parameters actually weren't as accurate. So we started with the Gaussian process using Cellularity, which nicely model things from the frequency space. So you have 3 free parameters: the amplitude, the frequency, and the Q quality factor. If you have a large Q, you have sort of oscillation kind of behavior with a strong frequency feature like this. So this is more like term. And if you fix Q at 1/√2, that's a typical granulation behavior that looking like one of the flatter curves over here. So what we had for our light curve were just 2 granulation terms and 1 oscillation term, which seemed to fit the data reasonably well. We did not have to invoke an additional one. All right, and then the question is, okay, you learned these parameters from the light curve, except for the amplitude, and then can transfer it to the RV and just fit the RV, right? And the answer is, well, yes, very easily, right? So this is a fit to the RV data simultaneously taken with the Kepler K2 light curve. Unfortunately, due to snow and telescope issues, we only had a tiny 2-hour section instead of a whole night of observation. So we only caught like 1.5 of the oscillation phase. But either way, we only had to float things like amplitude of the oscillation and also a white noise jitter term. And that's all. That's all the free parameters. We did not have to invoke granulation in this model, which I'll come to in a second. Okay, so one fun thing you could do when you fit Gaussian process to your light curve and RV in this way is that you can compare the amplitude in both signals very easily. And there is theoretical prediction what the ratio between the RV oscillation and the light curve oscillation should be. And this very simple fit is consistent with the theoretical prediction, so that's very nice. As you can see, the RMS around this fit is larger than the reported RV error bar, which is 0.78 meter per second. This is the residual RMS is twice of that. Of course, there is unaccounted systematics from the instruments probably, but also likely maybe this is some other correlated noise. I don't know, granulation that it just could not fit in the data. So that's yet to see. All right. Just to quickly show you power spectrum. So Eric, this is what I meant when I said I want to see a power spectrum. So on the right is the power spectrum for the light curve, where you can see clearly the oscillation peak over here, and then maybe a supergranulation term. We don't know. It could even also be residual systematics from the Kepler light curve. And then the granulation, which is fairly clear from the photometry, and then a small white noise component. But if you look at the RV power spectrum on the left, you just could not really tease out a very good granulation component as clear as in the photometry. And because of the limited amount of data, we could not test any models to fit granulation in this just small 2-hour section. So we moved on to TESS. But before we move on, I just want to quickly show this result from Nadege last year. to scare everybody about granulation and supergranulation, which you might have seen already. So Eric was saying that supergranulation is probably something that's really, really hard to beat by just averaging things out, right? And this is a work showing it. So Mounier and Lagrange, not last year, sorry, 2019, had extensive simulations of data over 10 years, meaning 1 hour per day of observations with some fairly realistic sampling over each year. And this is the detection limit in Earth's mass as a function of your observation hours total over the 10 years. And different curves are just for different habitable zones, and the points are for a different sampling regime. And on the left is a pretty moderate assumption of the supergranulation amplitude. On the right is a conservative, a low supergranulation amplitude, and this has granulation, oscillation, and supergranulation. As you can see, basically, with 10 years of data, you can't, well, in some cases, you barely reach, their detection limit barely reach Earth's mass. But it's quite a struggle. Your recovery rate is like only half, even in low assumption about the supergranulation. So supergranulation, I think, is something really scary that we ought to think about a little more. But back to RV TESS. So after that initial result with K2, we took more data with TESS because we hope to understand whether we can do this over a longer time scale on a variety of stars, because back then solar data were not as readily available. And then if we sample our RVs over a time scale that's longer than the mode lifetime, which the mode, for the modes that you characterize with the photometry, for example, can you still do that, right? And also with poor sampling, right? With the sun, we always have perfect sampling, but with real stars, we cannot do that. So we want to test in real world if you have poor sampling and limited amount of telescope time, what will happen? So we took on a couple of more subgiant, and this is one of them, HD 5562. Initially, from the stellar parameters, we thought this is something with a new max of 14 minutes. So we designed everything according to this, although it turns out it's not. We'll come to that later. So we had roughly 60 days of observation simultaneously with TESS, sector 1 and 2. And we have 2 nights of high cadence observations where we just stared at the star with Magellan, PFS, for the whole night. And then in the nights following or preceding the high cadence night, we had some sporadic observation that just covered the star for a duration of 1 hour new max, roughly 40 minutes. Okay, so we had 2 sections of high cadence data, 20-30 days apart roughly, and then few nights of sparsely sampled data. And then we started our Gaussian process with the TESS light curve, which turns out to be something very challenging because TESS is not like Kepler, it was very noisy. So this is a zoom in to the power spectrum of TESS sector 1. Possible due to my amazing career student Jiaxin Tang. So if you look at the TESS power spectrum, you can clearly see the sharp peaks due to stellar oscillation. But if you look at the overall power spectrum, they're pretty much buried in noise. So this is something very challenging for Gaussian process to pick up if you just have like one broad, like Eric mentioned, the Gaussian-like shape-like oscillation term. But nonetheless, you can still do it. Right now, we're trying to fit these separate peaks jointly together. This is actually has been done with Cellularity on data with similar noise ratio. So we think it's going to work. But for now, we're just fitting, again, one broad oscillation term on all of those signals, and then transfer that model again into our RV. So this is one of the high cadence nights. As you can see, again, very, very easily, it fits the data very nicely and reduces the RMS by a factor of 2. So the raw RMS of this was 2 meters per second, but the bottom is something like 0.8 meter per second, which is very, very close to photon limited errors. The error bars on these are roughly ½ meter per second. Okay, the star has a new max of, it turns out to be 15 minutes instead of 40 as we originally thought. So we were very close to Nyquist on some of the nights. But nonetheless, it still works because you already know what is nu max from the light curve. I just want to quickly show that how similar this is to sun-like stars. And probably in the sun, sometimes you have modes beating constructively against each other, and sometimes you have a flatter part. The sun and the sun-like stars, of course, have a nu max of near 5 minutes, but this star is just totally analogous to that. So this is a good test for something like our sun, but not as, quite the amount of data and cadence as the solar sample, stepping away from the sun just a little bit. Okay, so this is a look on the 8 different days of our data. Remember, from day 4 to day 5, there is a gigantic, day 3 to day 4, there is a gigantic 20-day gap. But even with very sparse sampling, Gaussian process can sort of continuously feeding data over this long time span. Of course, the 2 high cadence observation sections helps a lot. So just a quick summary. So we started with TESS photometry with 2 granulation terms and 1 oscillation terms, and we transferred the models from the light curve into the RV model, where we have just 1 granulation. We found that we did not have to include the supergranulation in there, and then 1 oscillation with now we have 3 parameters, 3 free parameters, 2 amplitudes for granulation and oscillation, and the quality factor for oscillation, it turns out we have to float that because a broad peak fitting the light curve is just not a super nice approximation for what's actually going on for this star. I think once we fit the 4 very narrow peaks, this is going to work better. The RV clearly likes a different structure. All right, and then a jitter for the white noise. All right. As you can see, it works very nicely for feeding the RV. Again, beating the noise by a factor of 2 and larger. And what we found out is that because of the high cadence observations, you can actually float the frequency for the oscillation, because you don't have to really tell it from the light curve to be able to find nu max from the RV data itself. Next, we're gonna eliminate the high cadence ones and randomly draw points from them and see how things will turn out that way. All right, so this is still very much work in progress. But again, what surprises us next is that with this much data on a subgiant that's significantly larger than the sun, we still could not pick up the granulation signal. So this model I'm showing you here has granulation, and we're forcing it to be the same as the one from the light curve, just fitting the amplitude. And really, you can get rid of it. It does not need that to fit the RV very well. So this is, again, zooming in on the last day with the high quality, high cadence data. This is our fit with that 1 granulation term, and the bottom plot showing the one without granulation. And the overall RMS over the course of 60 days are basically the same between these 2 sets of models. And the residues, you can only see like maybe a tiny bit of difference. If you squeeze your eyes, maybe this has like a little more structure, but I'm not convinced that granulation is absolutely needed in modeling this. So we're pretty disappointed that even with this much data, you can't really pick up the granulation power. So I wonder if the answer is we really need something analogous to the solar data to really see this. Okay. So then finally, the conclusion, maybe I think there are more questions than conclusions for me, at least in this project at the moment. We now know for sure that GP provides a really good fit to the oscillation and granulation signals, at least in the light curve. In the RVs, I guess only in the solar data we've seen this. And the photometry is, of course, very helpful. You can tune things on that. You don't have to rely on the knowing the stellar parameters and the precision, accuracy of your theoretical predictions. But we've done some tests, and it turns out even, with that gigantic gap after, the modes died, beyond the lifetime of the modes, you can still model it as long as you know roughly where new max is. So we feel that simultaneity is perhaps not required in this type of work. We have not found significant correlation in the phase of oscillation for our more pronounced subgiant. But I think that's something to explore, is whether, just like magnetic activity, whether oscillation signals would have some sort of phase correlation. That's yet to see. And then finally, we have those free parameters Q. Sometimes we can freeze Q, the quality. Always you have to flow the amplitude, but again, our model actually matches the theoretical prediction of the ratio between the amplitudes of RVs and light curves. So we're wondering, if you ever have the light curve, you can perhaps even eliminate this free parameter by just telling it how much it is. But it's probably very hard to get it to the precision you wanted, especially we're shooting for something like 10 centimeters per second. So this is probably the last free parameter that's going to be super hard to get rid of. And then again, coming back to a more realistic sampling for real observations, where we cannot always afford high cadence observations. And perhaps, like Eric alluded to at the end when he was answering questions, that maybe once a year you want to just sit on your star for a few hours, right? And then it tells you a lot, and then that sustains you for the whole year for, I think, mostly oscillation. Now I'm just not convinced that's enough for granulation. Okay, and then again, Gaussian processes are just very handy for test models and theoretical scaling relations with these stars, especially giant stars. You don't have to do the awkward measurement in power spectrum and convert unit and normalization and all that. Everything is just very natural with Cellularity's Fourier space kernel. All right, so that's all from me. Thank you very much, and we welcome collaborations.
Thank you, Sharon, for a really nice talk. Maybe it's a silly idea, but when you're trying to find the granulation for that one star that you put into it, have you tried sort of bidding optimally to squash the P modes and then look at what's left and see if there's a signature of granulation that's remaining?
That's a great idea. We're gonna do that next. So for that one star with K2 observe the Keck, we only have like an hour and a half over the course of 2 hours. I suspect that's gonna be tough. But for the other 2 stars, we have more data. We're certainly gonna try that. Thanks for the suggestion. But again, like Eric said, oscillation and granulation really operate on very different time scales. So if you just look at them in the Fourier space, right? If you have enough power to just identify granulation, it should jump out because they occupy a very different space in frequency space. But we don't see that. So, but it's probably too early to tell. We'll report back. Thanks.
More questions? So questions on yeah.
Hey Sharon, what's the ongoing status of RV TESS? Are you still, as TESS continues observing, trying to do more simultaneous observations, or is the data you mentioned before kind of the starting point for this, and you're going to assess that before doing new observing runs?
Yeah, so yeah, that's the sad story about this project, is that I got distracted into other things, like Magellan test theory. So we are not proposing new observations since we're sitting on so much data. But there are other folks who have been proposing to observe simultaneously with TESS to do similar things, like Paul Roberson's group at UC Irvine. I think they mostly use something like NURD and target things like active AMDORs. But I haven't heard the latest. Perhaps Eric knows about it. So I have another student right now working on the spiral polarimetry, polarimetric data to see if that's helpful. If that turns out to be helpful, just like Raphael showed in her paper, right? The unsigned total magnetic flux from the sun is a really good correlator for the RVs. If this works out, I think we're gonna do more of the Amdorf observations. But for the other things, at the moment, it's unclear how we would carry on until we finish sifting through this data. Thanks for asking.
Any more questions? No. So thanks, Sharon, again.
Great, thank you. How can we end?